Okay, so in this example we have a beam. We have same thing, we have the beam and it's connected to a roller and a pin, right? And over here you have a pulley applying a normal force, 400 newtons, right? We'll assume that's a frictionless pulley. So the steps to this are that you determine where you have to take the imaginary cut. So let's say you have to take an imaginary cut at point C. And we'll just label these points. This is A, C, you have a B over here. And each one of these would have representative distances, right? And you'd have representative heights as well. So to do this, what you do is you, again, figure out where that imaginary cut is, and then you want to determine the internal forces. You want to determine the support reactions or the joint forces, and you draw the free body diagram of the entire structure, right? And you draw the free body diagram of the piece of the structure. So in this case, we'd either draw it for that section or for this section that we're going to cut away, right? And then on the free body diagram, you want to have the normal forces and the shear and the bending moment at the cut surfaces, right? And you want to be able to show it from both sides. And then you want to apply summation of the forces, and the summation of the moments should be equal to 0, right? So moving right along, the question in this case would be find the internal forces at point C, right? So I'm going to redraw this whole thing just for clarity. We have this piece here, pin connection and the roller connection, and we have load here 400 newtons, right? And you have the cut at C, pin at A, and the roller at B, right? So how would this look? I need to get colored pens, eh? Well, I think I can hook that up. Let's see if I can manage to do that by the next go around. AX, and then you would have over here, you'd have some normal force, and then right here you'd have some force being applied of 400 newton, and that's the overall body, right? So equations of equilibrium in this case would give you some forces in the x, some forces in the y, and then what would we have? Some of the moments, right? So if we sum the forces of x on both x-axis, AX would be equal to 400. Everybody agreed? I hope so. Well, assuming that this is a positive force, we would then say that AX is actually negative 400, right? So the real equation should be AX plus 400 would be equal to 0. So AX would be equal to negative 400. And the units, again, are in newtons, right? The next thing that we could do is sum the moments about B. And remember when we said the forces are acting along, and there's no perpendicular distance, we don't have a moment to consider when we're taking into consideration that particular different forces, right? So sum of the moments about B would give us AY, and we know that this distance here is 3 and this is 2. It's not shown very well in the image, but AY multiplied by 5 would be, well, let's say that's, what's that going to give us, clockwise or counterclockwise if we sum the moments about B? We use the right hand rule, so we roll it we'd say that's clockwise, so we could call that positive, right? And then you'd say here that well, what? Actually, this would be negative, and we'll say that's positive. So we would say that 400 times this height here is 1.2. 400 multiplied by 1.2 would be equal to 0. I'm not sure if that's coming across very clearly. Oh boy. I'm a novice at this, so you have to bear with me, right? 400 times 1.2 minus AY times 5 would give us 0. So AY, if you solve for it, would be equal to 96, but it would be negative 96, right? So AY would really be pointing downwards. So that you have the two moments. This moment cancel out that moment, and that's newtons.